Hey pre-calc students, so far we have been talking about the graphs of trig functions and their reciprocal trig functions. So we have looked at graphs of the following. Sine and sine's reciprocal cosecant, cosine and cosine's reciprocal secant, and tangent's reciprocal cotangent. For all of these functions, the input of these functions, x, is always representing an angle, and the y values are always representing the trig value. For today's video, we're going to be looking at the inverse functions. So we're going to be looking at y equals sine inverse of x, y equals cosine inverse of x, and y equals tangent inverse of x. It's important to note that in an inverse, the input and the output have been interchanged. So here, when we say the input value x, it's no longer the angle, but it is a trig value. And the output of these inverses are angles. We're going to predominantly look at these angles in radian mode, but you can also do these in degree mode as well. Okay, just a quick recall fact about graphs of inverse functions. So whenever you are graphing an inverse function, you're find inverses by switching the input and the output. Input is usually x, output is y, and then you normally solve for the new output y. Their graphs are always going to be reflections over the line y equals x. So for instance, if I have a graph of f of x and I use the graph y equals x, if I graph f of x's inverse, like I have here, g of x, we can say that these are reflected over this line y equals x. And again, this is what graphs of inverse functions will always look like. So if you're ever wondering if two functions are inverses of each other, you can always graph them and the line y equals x, and it should be a reflection over that line. Before we talk our trig inverse functions, I want to take a moment and talk about what happens when the inverse is not a function. So we've seen this before, in our usual case where we've run into this is with our quadratic function. And the quadratic function inverse, so again, remember that notation of an inverse is the f to the negative 1 of x, that means inverse, is the square root function. So we've seen these functions before, and I just want to quickly talk about the graphs of these functions. Okay, here I have the line y equals x graphed. I'm going to add to that the quadratic function, so y equals x squared, and then I'm going to create the inverse by just switching the domain and range. So switching the x and the y values, I'm going to add this graph onto my Desmos graph. Okay, you can see that my inverse graph is a reflection over the line y equals x. And again, all I did was change the input and output in my Desmos. But the issue with this graph or this expression or equation is that it is not a function. It fails the vertical line test. If I were to have an input of 4, the output would be both 2 and negative 2. And for coding and a lot of times where math is very applicable, what we need is an input to only yield one output. So this is not a great thing that this is not a function. So what we're going to do is we're going to limit the range of this function or limit the range of this equation so that it can become a function. Okay, and so here we have the actual inverse function, y equals the square root of x. Notice that it's only the top part of the inverse expression. So now it has become an inverse function. So again, just kind of like maybe using some names here, we would call this an inverse equation. And we would call this the inverse function. And again, a lot of times in math, we want the inverse function. So the inverse function is going to match the inverse equation, but it will have a limited range. Here, the range of the inverse function has been limited to only positive values. So we say that the range is from 0 to positive infinity. This is also why when you take the square root of a number in your calculator, it's only going to ever return the positive number. And it will never give you the negative number because, again, we want a function to only return one output, not two. Okay, so why that conversation was important is whenever we're graphing trig inverses, it's important to know that first, the original trig ratios, sine, cosine, and tangent, are functions. This is true because every angle is only going to have one sine, cosine, and tangent value. However, the inverse equations or inverse are not going to be functions because the sine value can come from multiple angles. For example, we've seen this before. We know that sine of x is going to equal 1/2 when the angle is 30 degrees or the angle is 150 degrees. So we've seen this before, that sine value, and you can see this on your unit circle, we can have multiple angles that yield a sine value. So when we start talking about the sine inverse, the sine inverse could have more than one answer. It could be that the angle could be 30 degrees or the angle could be 150 degrees. But because this is not function language, we only ever want to use the primary angle. So the angle that is primary will always take over than the angle that is secondary. And we're going to talk about how does this look on a graph. Okay, so here I have my sine function, my parent sine function. I also have the line y equals x. And so now what I'm going to do is I'm going to create the sine inverse equation by changing my x and y, my input and output. Okay, here I have graphed the sine equation, but notice this sine equation does fail the vertical line test. It has multiple y values for a single x value. So because this is not a function, we're going to limit the range so that we can create a sine inverse function and not just a sine inverse equation. Okay, so here I have my cropped sine inverse equation, which creates a function now. So now this function does pass the vertical line test. So now I'm going to clear the screen of everything but the sine inverse and talk about some special features of the sine inverse equation. The domain of this teeny tiny function is between -1 and +1, and the range of this function is from negative about 1.57 to positive 1.57. These are actually just rounded values of pi over 2. And again, the domain is -1 to +1. This function is increasing as we move left to right. And it is continuous on its domain. So it does stop, right? These are closed circles. So this ends the function. It doesn't like continue on to negative infinity and positive infinity. But when I say continuous, I mean it has no jumps, it has no holes, and it has no vertical asymptotes in its domain. So this is a continuous function. One last key important identifying feature is that this function does intersect the origin. So the point 0, 0 is both the x-intercept and the y-intercept. Sorry, I said that was the last, but I also think it's worth talking about because this is a closed and bounded graph. It does have an absolute max and an absolute minimum. The absolute maximum value is going to be at 1 pi over 2, and the absolute minimum value is at -1 and negative pi over 2. Okay, we're going to repeat this process for cosine. So in blue, I have the reflection line y equals x. In purple, I have the parent function of cosine of x graphed. And then in black, I have the inverse equation of cosine, which is the reflection across the line y equals x. You can see it's a reflection across the line y equals x. So this is the inverse cosine equation. I'm going to crop this so that we can talk about the inverse cosine function. Okay, so now I have just the graph of the inverse cosine equation and the section of the graph that we're going to use to create the function. I'm going to now clear out the cosine equation and talk specifically about the cosine inverse function. Okay, cosine inverse function has a domain from -1 to +1. It has a range from 0 to just over 3, in fact 3.14, which is pi. It is decreasing on its domain, and it is also continuous on its domain, meaning it has no holes, jumps, or vertical asymptotes. It is a closed function, and it is bound by its endpoints, so it does not continue to infinities. It is very restricted by its domain and range. This graph also has some key identifying points as well. It has a x-intercept, a y-intercept, an absolute maximum, and an absolute minimum value. So I think that's worth writing down too. Okay, so the y-intercept is at 0, 1. The x-intercept is at 1, 0, and this point is the absolute minimum on the graph. And then the absolute maximum point is at -1 pi. Okay, last graph that we'll talk about is the tangent inverse graph. So again, going back to the original, I have the reflection line, y equals x. I have the tangent graph. The tangent graph does have repeated shapes. So we've got the tangent graph that repeats. It's broken up by vertical asymptotes. Some of those vertical asymptotes we've explored already. There's one at pi over 2. There's a vertical asymptote at 3 pi over 2. There is and those will continue. So we've got tons of vertical asymptotes all throughout this graph. I'm now going to graph the tangent inverse equation where I switch the x and the y. And if I'm being honest, this is kind of a mess, but we're seeing that all this is I have reflected the purple tangent graph to create the tangent inverse graph, and it is a reflection across the line y equals x. This fails the vertical line test, so I am going to limit and crop this equation to create the tangent inverse function. Cleaning up my graph just a tiny bit, now I just have the tangent inverse equation, and the selected range, or the cropped range of the tangent inverse function that I'm going to use is just this one piece of tangent inverse. Okay, some special features about the tangent inverse graph. It does have an infinite domain. This function will continue to positive infinity and negative infinity on the x-axis. The range is limited by 2 horizontal asymptotes. So this graph has got a horizontal asymptote, again, just over 1.5. This is actually pi over 2. And again, another horizontal asymptote at negative pi over 2. So it does have a limited range, and these values are not going to be included in the range because they are asymptotes and we approach them, but we don't actually reach them at the ends. Other key features, this graph, as you move left to right, is going to be increasing. It has a x and y intercept at 0, 0. And then we'll also talk some end behavior on this graph because we do have arrows that continue. So we will talk about those in terms of limits. But let's write down our domain, our range, increasing. This function is continuous. It has no holes or jumps or vertical asymptotes within the graph that breaks this function. And then some of our key points, in other words, like the origin point, it crosses there. Okay, and I think the last thing worth really mentioning is the end behavior of this graph. I know this becomes kind of important, especially if you study this graph in calculus. It does have a limit to it. So the limit, as our x values approach positive infinity of our tangent inverse, is going to approach the positive pi over 2, that positive horizontal asymptote. And if I find the limit as x approaches negative infinity on this graph, I'm going to approach the negative horizontal asymptote of negative pi over 2. Okay, that covers all trig graphs. So again, we've covered sine, cosine, tangent. We've also covered their reciprocals, which is doing 1 over those trig functions, which is secant, cosecant, and cotangent. And finally, now we've added our inverses of inverse sine, inverse cosine, and inverse tangent. There is an activity for you to try where you are looking at these all 9 trig functions and the transformations on those. So give that a try.